way to the beginning of 8.1 part 2. Yesterday, we talked about parabolas, and what was different yesterday, those parabolas, those swoops, there they are, either concave up swoops or concave down swoops. Different than the exponential growth. Having that full, Isaiah and Armand, just go quick. I think we can do hand sanitizer. With the concave going down or the concave going up, was that they gave us the graph and we were answering questions about it. Who's this little R again from yesterday? All real numbers, everything, forever. Infinity is, I think, Adrian, you were telling me the sideways 8, right? If we're going forever, we can use the sideways infinity. But the awkward part of that is we would have to talk about infinity that way versus infinity that way. And now there are different types of infinity. That's kind of crazy and big and blows your mind a little if I were to keep talking about it. But there are different degrees of infinity, and different directions of infinity. Anyway. Countable and uncountable infinities. Too much. But anyway, long story short, we could have explained it with those sideways 8s. It's just harder because you can go infinitely far that way, but not that way. So how do we describe going infinity both directions? It's easier just to say all real numbers. Either all real numbers, 3 different words, or the little snazzy symbol. Range. We're not talking about how far left and how far right, like x values. Range, we're talking about y value, and what's true with any parabola. If it's concave down, there's a highest height. If there's concave up, there's a lowest height. Good. So this one had a highest height, which means the y's have to stay below or equal to, it's going to hit below or equal to the highest height, and the highest height was the highest y set. Okay. Inequality says you got to stay below.
For all real numbers, you put A.R.#.
That's okay too. I'll understand it. Some people do ART. No, ARN. All real numbers. And then Isaiah just asked a quick question about that increasing, decreasing thing, just to clarify. So let's clarify us too. Increasing, decreasing. We aren't talking about where the curve is. We're talking about how the curve is moving. Now, I know it's a little bit weird because we were using the basketball court yesterday. We can kind of use it again today. Just because, like soccer, I mean, the ball does go up and down. I guess it could be something. Yeah. Tennis, it goes up and it goes down. And then, well, cross country, you go up and you go down on all your switchbacks. But anyway, coming back. Basketball's a little easier in my brain. Could you be shooting towards the basket this way? Yeah. Or that way? Yeah. I mean, during the game, you switch directions anyway. Like, it depends. In basketball, the motion could be moving 2 different directions. But in math, when we're discussing a graph that's just like there, set, solid, not actually moving, just talking about the path of motion, we only go one direction. And the only direction we go is from left to right. Like you're reading a book. So as you're going left to right, what we're trying to talk about is where are the heights increasing, are the heights going up, and where are the heights going down? So if you're moving on this path, aren't you going up anywhere to the left of -3? You're going up anywhere to the left of -3. And then what happens as you hit that -3x marker? You start going down. And so the increasing, decreasing is saying like, oh, hey, the heights are going up. Sweet. Which direction? This way of -3. And the little inequality shows us less than -3. And then my heights are falling, decreasing anywhere right of -3. And the little arrow, the little inequality, the greater than, shows us that. That was yesterday. Today, guess what? The graph's missing.
Nice.
Which means we have to make the graph to be able to do any of the analysis we just talked about. But the nice thing is, not everything is missing. They give us an equation at the very, very beginning. So you guys should have a table made, true? What do you always do at tables?
You put the X in.
Put the X where?
In the X.
Exactly. Plug it in, plug it in. Pretty old substitution, but there is one key mistake that so many of you are going to make. You ready? I need you to rewrite this f of x equals parenthesis x squared. Because PEMDAS, would say when you plug in, that whole number has to be squared. The entire x has to be squared. It might be silly, and maybe very few of you would make that mistake. But put those parentheses around the x to show where am I plugging in? Right here, underneath or inside the squared. So if we need to, I mean, easy cheesy, it's a -2. Well, the easiest one would be 2, right? What happens if we throw in 2 and square it, guys? 2 times 2, which would be the same thing as, got him. Now, if it gets harder and longer, we might have to show our work, but I'm guessing most of us can square at least the smaller numbers, right? And some of you already filled it in. 1 squared is just 1 times 1, which is, got him. 0 squared.
0.
Got him. Andrew, why are you confused? I see that.
No, I just thought, like, how do you get 4 how do you get 4 when you answer 4?
Well, remember a table is giving you set x values that are locations on a graph, but we don't know the y values. So maybe it'd be helpful for us to remind ourselves that at y equals f of x. To find the y values, we have to plug into this guy's equation. And so we have these x's, but we're like, we don't know where to put the point at -2 or at -1 or at 0 or 1 or 2. So we have to come up to the equation and say, hey, who's the y? We know the x, they're right here. Who's the y? So we're taking each of these and plugging in. I'm just working backwards because it's a little easier to square 2 than -2. And I'm squaring it because, look at your equation. Where does the x go? In the square. You see it? So 2 squared, if I was to actually substitute, it would be a 2 squared, which made 4. Or it would be a 1 squared, which would make 1. Or it would be a 0 squared. So guys, what happens when I have -1 squared? +1, because a negative times a negative is a, everybody knows, yeah? And then -2 squared, that's why I showed those parentheses. 4. +4 though, yeah? Now, sketch me points. And I only did a few. Guys, you saw this go to -10 and 10. Maybe you can keep following a pattern that you're going to see. Sketch your points, because now you have x's and y's. Remember, the x's are how far right or left you go. The y's are how far up or down. I heard this example at one of those nifty math seminar things I went to this last weekend. Yeah, this whole conference I went to, which is when you guys are taking your test. That, to graph a point, you just have to think of, you're walking into like one of those big old skyscraper buildings, but on the bottom floor. So you got to walk to which elevator are you going to go up? That's the x. And then what floor are you stopping at? That's the y. Which elevator are you going to? -2's elevator. That's the x. And which floor are you going up to? It's kind of silly, but it works. The x tells you which elevator to take, and the y tells you which floor to stop. Now, hold on, wait a minute. How'd you graph -1? It's not on my graph. Oh, yeah, when you have like distances of 2, just go halfway. So -1 is going only up to a height of, you guys get them in the approximate right location? 0, 0. What are you noticing about the points, guys?
Pattern.
It's a pattern.
It's a V.
It's your, well,
That's
kind of.
U.
It's a U. So, there it is. Think a yo-yo, and then comes back down, but maybe you're like swinging it out. Or it could be someone swinging. The swing only goes so high, although this would be off the ground a little bit. The swing wouldn't be on the ground, that would hurt. The swing would be up a little bit, but it could be someone swinging too, right? So it'd be a little bit wider, I think, if it was a swing. Now, we didn't keep plugging in numbers, but do you guys think you could kind of graph for me the whole parabola, like with arrows to say it keeps on going?
Yeah.
And if you needed to, couldn't you say like, oh, hey, if I was going to 3, where would 3 be?
Right there.
Why would it be up to the 9th floor?
Because you multiply.
Because you have to square it, right? But I didn't make my table too big, because as soon as we get to 4, now it's supposed to be going up to, it's too high. It's too high for my graph. But some of you might be seeing this thing called symmetry. Ooh, that's a snazzy word. Lines never have symmetry. Remember yesterday we had a line up? Lines never have symmetry. So you probably never really talked about it too much back in Algebra 1A, but parabolas have symmetry. If you guys notice the pattern going on, what can I put right away on this other side for -3 without even thinking about it? Same thing. Just go over and copy it. Say, there he is. And and then swoop. This isn't like those crazy sequences that we were doing where we had to just do the points and stop. Nah, we can square anything. I could have given you a 1/2. If you had plugged in, it would have been kind of awkward and in between here and here. But if you had plugged in a 1/2 times a 1/2 is a 1/4. All numbers, and that's really awkward to be like way down here. But the negative 1/2 would have a 1/4 too. Any number can be squared, so all the numbers get to be included, hence I connect it. But swoop, there he is. So question, who is this guy's domain? And if you want to be snazzy, mathematicians, kind of lazy but efficient, they like shortcuts, but they have to make sure that it's still right. You can write a D for domain instead of D-O-M-A-I-N. D for domain. How left, how right will this guy go? You can look back to yesterday's notes. All remembered. Yeah, good. Forever left, forever right. But question, does he have a highest point or a lowest point? Lowest point. And what's the lowest he goes?
Negative.
Yeah, it's hard. You have to think of, wait, is she asking for the x's or the y's? Which is why we always started the other examples by writing the y to remind us. And then you can look at the y values on the y-axis. What's the lowest height he hits? 0. And then how do we show that he's going to be above or equal to? There's that greater than or equal to. 0 is the lowest he goes. Remember, those inequalities point to the smallest number. What was another question they would have asked us, like in the homework? Increasing. Good. Increasing and decreasing. You guys see me being all efficient but kind of lazy up here with I and C and Sweet. Increasing.
2.
Now, careful. We've got to remind ourselves, we're talking about x's, so we're going to write the x's. Because that helps our brains like reorient. Because the increasing is what the y's are doing, going up, or the decreasing is what the y's are doing. We have to look down here and say, when does that happen? So, 0 is where the switch happens from going down to going up. You can find the valley or find the mountaintop. Those are always the places where it switches. So what's going on before 0 as you read the graph? It is which one? Decreasing. That direction. Oh, so use that arrow and saying, hey, that way it's decreasing. Oh, decreasing. My bad. That way it's decreasing. There we go. So what inequality am I going to use for the increasing? And guys, there are totally patterns. Things like anytime you have a vertex, that x is always going to be the same number as this one. And that, see if I change the color real fast, that y, it's always going to be the same number as this one. There's some patterns. And maybe you guys saw it yesterday when we were doing those ones with domains. And I'll come back. Domain and range and increasing and decreasing. You see how the x, we used it for the increase and decreasing. See that? And where did that 7 come from? Wrong one. From the y. Right? So that vertex is a super important point. He shows me either the highest or the lowest he goes with this little y value right here, but he also shows me that little separator between the increasing and decreasing parts. And I know it might be like, okay, this is dumb, it's a parabola, what's going on, blah, blah, blah. However, remember, we talked about yesterday how parabolas can model more real-life movement. And if we're talking about things like business and economics and money, like people think money is pretty important, and we don't disagree with them, right? And if they want, like, their investments, the value to be going up versus going down, they want to figure out where it's the highest, but before the value starts falling or crashing. Anyway, these are really important points to put. Yeah.
Oh, I'm still kind of confused on how we got the increasing and decreasing part.
Okay. Well, we're looking at the graph, and basically, Andrew, I think this is the easiest way to think, okay? Anytime you have a parabola, I want you to picture, and I know it's kind of silly, it really is, but I want you to picture that you're on a hike, okay? If you're on a hike, the only direction you're ever allowed to be going is from, I guess in a compass, from like west to east, right? So you're only allowed to be going left to right, or if you're on like a compass, west to east. And I'm just asking, is your elevation falling? Or the height's decreasing? Or is your elevation rising as you keep on walking? So what's this little guy doing on this entire branch? The elevation's fallen, right? But his height above the ground, above the valley, he's getting closer and closer and closer to that bottom. The heights are decreasing. So I just need to figure out a way to explain that. And the way that we explain that with math is we talk about for what horizontal values or what locations on the mountain he's on. And so to use that, we use x's, and the easiest way is to see, we always figure out where the valley is as far as the x. And then we just use the inequality that points the right way. So where is he decreasing? He's decreasing on that part. Check out your inequality lesson. So then where is he increasing? Well, as soon as you get down here and start climbing the mountain, oh, it's increasing. And where is that? This way. Check out your arrow. That's like a silly way of remembering, but it helps. Yeah. And basically we're getting used to new notation. That's it. Yes. So cool, kids. What would happen? What would change if we were to put, I think we only have like 2 examples up here. We have a couple. Let's actually skip ahead to these guys. I'm going to make it a little bit bigger so that we can see. We could have done a few other examples, and we'll look at tables that are already plugged in and be crazy that are doing stuff behind my back. Stop. But let's just keep the tables blank. Because technically in homework, you're not going to have anything for these graphs. You're going to have to make it. So how do you make it? The table is completely blank. What do you guys think? Yeah, find x's first. Find them? No, just make them up, to be honest. So we have options. What do you want to use? Yeah, sure. We can use -2, 0, 1, 2. I don't mind. It's -2, -1. Did we have to use that? No. We could have used -10, -5, 0, 5, 10. Could have used -1/3, 0, 1/3, 6, 9. I don't know. I'm making up stuff, but we could have used any of the x's that are in the. Okay, my graph only goes from -6 to 6. Probably a bad idea to use stuff outside that. But what's my equation this time, guys? Yeah, g of x is equal to 5x squared. Now we have this big question at the very top of the page. We're going to graph and compare to that little original guy that we started with. But for right now, before we can compare it, we got to graph it. So I need you guys to come up here, and when it says g of x equals 5x squared, I need you to put in that parenthesis that shows me the x location. Remember, x marks the spot. X shows me where to plug in whenever I have a variable. And so some of you, it's a little easier if you say, where's x? Oh, he's right here, after the 5 times and inside the square. So for this guy, I'm going to go ahead and plug in. Well, let's start the easy one. Okay. Let's start at +2, not -2. PEMDAS. PEMDAS, what do I do first? 10! I don't multiply first. What do I do first, guys? Parentheses with the exponent, right? E before m. That's 5 times. Forget him. That's 2 squared. Got him. So what's 2 squared? 4. Now do your times. How good is my graph going to work?
Not good. That's about.
Okay, so what do we, well wait, you're allowed to make your own graph, aren't you? Yeah. What would be smarter units for me to, like just going as high as possible, what would be smarter? 5s? Sure, so let's go ahead, maybe you guys should change yours too. 5, 10, 15, that's a much smarter idea. Okay. Okay, that looks weird with that 5 being that way. Hold on, there you go. Yeah, let's go by 5s. But now if you plug in 1, what's gonna happen? 25. What do we do first? 5 times 1 or the 1 squared? 1 squared. So what's 5 times 1? Okay, keep on filling in the table. Make sure you got it right. If you finish your table, then start plotting your points. If you can plot your points, then say, how did this change from the one that we just looked at? get your points, think about how did this change from the one that we just looked at? Focus. You guys plugged in 0, and hopefully you got out 0. Plugged in -1. Did you realize it's still +5? Plugging in -2, did you realize it's still +20?
Let's go.
Because a negative times a negative is a positive. And if you came down here to the graphs and you remembered each x is what elevator to go to, each y is how high, what floor to take. Maybe. Just maybe.
That's you.
You would have gotten a parabola too. Wait a minute. You're not thinking super carefully. You might be like, this is the exact same as the other one. Does it look the same? At a quick glance, yeah. To you? The 0, 0 looks the same to me. But is it the exact same?
No.
Look at your tables. They're asking us to graph and compare. We have to figure out a snazzy math way of describing what happened. Can anybody see any difference between the one that we just did and the one that's on the screen right now? Either looking at the graphs or looking at the tables. Andrew Bosch, what do you see?
We had to like times it.
Well, we had an exponent in the other one, but I do like what you said. You said we had to times it by, what was extra in this one?
5.
The 5 times, right? The multiplication of 5. Now, question, guys. Do you still have a guy at 0, 0?
Yes.
Yeah, that didn't change. Do you still have it going up?
Yes.
That didn't change. But how high did it go? Question, when you were at 1 in the last one, how high did you go?
4? No, 2.
2 went to 4, right? 2 only went this high, and 1, so if we were to graph the other guy, he was like here, and he was like here. Now, it didn't look that way because of the way we did the units. But what happened? This was the old guy. He would have kept on going this way.
It was wider.
It was wider, so think about it, okay? If this was a rubber band, the blue one, if it was a rubber band, what did you do to get from blue to red? It was a rubber band. You stretched it. Exactly. Ready? This one is a vertical. Why? Because which way are you pulling it? Vertically, straight up. Is a vertical stretch by, and then Andrew, what did you say was extra? Multiplying by? 5. You want the snazzy math way of saying how this one changed that one? It's a vertical stretch by 5. Oh, so this is easy. All I have to say anytime they give me a problem is vertical stretch by the number in front, right? Yeah. What about this guy? Although, I'm not just going to say 1/3, I'm actually going to put in negative also.
Yeah.
Do I mean like that? Adrian was about to say a vertical stretch by 1/3. Wait a minute. If I say stretch, what do you usually think is happening? Getting longer or getting shorter? Longer. So if you're multiplying by 5, did my y's get higher? Yeah. That building that was only so high is now like, either that or you're on a super fast elevator. But either way. Okay. Why does saying the word stretch and then saying by 1/3 not really make sense? If you're multiplying by 5, everything gets bigger. Don't you guys realize if you multiply by 1/3, everything's going to get smaller? So then, is there another word that kind of means the same as stretch, except it's going the other way? Shrink. And that's totally how math terminology kind of works. Vertical stretch is going to be by 5. This one's going to be a vertical shrink. Guys, we can already write it down. We just had to kind of tweak what Adrian said. He was right. We are doing that whole vertical thing because it's still out here. We're using the by 1/3, but the 1/3 it's not going to be making it bigger. It's going to be making it. And with a rubber band, if you push down, doesn't it also go out? Right? If you pull a rubber band up, it gets narrower. If you push it down, it gets wider. So this is actually going to make it wider. But we're just going to say vertical shrink because we're talking about the heights. Now, what's the one thing I added, though? Before we finish 8.1, this is the last example of today. Before we get to practicing factoring for tomorrow, your retest. You gotta figure out what that negative is. So here we go. I need you guys to rewrite this. Where do the parentheses go?
In the X.
Good. All around that X, right? So when I go to plug in, I'm going to be thinking of this is the space I'm supposed to fill. Now question. Why would using -2 be an awful idea? Well, negatives are complicated. Why would using 2 be a bad idea? Not bad, but hard. Think ahead. Why would plugging in 2? Right? 2, 1, 0, -1, -2. We like 2. No, we don't.
Doesn't go into 1/3.
Yeah. No, better. Careful, Jared. 4 doesn't go into 1/3. Because what are we going to do before the 1/3? We're going to square it. But yeah, excellent. We have a 1/3 cube, 4/3. Who likes that on a graph? What would be a better number to plug in besides 2? 3. Right? So let's throw in 3. If you want to be snazzy, I guess we could throw in something else like 6 or anything else divided by 3. 5? No, 25/3 doesn't work. 6 squared. 36/3 would work. We just throw in 3. Let's throw in 3 and 1 and 0 and -1. 3. Why? Because I didn't want to plug in 2. Oh, thank you. Good catch, guys. -1/3 times 3 squared. Okay, PEMDAS. 9 times -1/3. What's 1/3 of 9 with a negative? You have 9 pieces. You're cutting it up into thirds. Does it help to do -9/3? -3. Careful. Yes, 3. 9/3 is 3, but we have that negative sign, yeah? Now hold on. You guys have been seeing patterns, true? Who else is going to be -3 without me even thinking?
-3.
Sweet. Let's save time. Okay, let's plug in 1. -1/3 times 1 squared. Ooh. 1 squared is 1. 1 times -1/3. Isn't it just itself? We still have a fraction. But at least we didn't have a fraction there. Okay. 0. Because 0 squared is 0. 0 times anything is just
0.
Good. Don't we already know what that
Yeah,
means?
same one.
Seal it. We have lots of patterns with parabolas. At least with easy parabolas. So guys, if we go to graph, we're going to have our 0, 0. I don't mind graphing -3, -3. I don't mind that. Or +3, -3. But what am I not doing and I'm avoiding? Like some of you guys avoid and don't like them.
-1/3.
Yeah. How do I do -1/3? Can we like eyeball it and approximate? Wouldn't it be like 1/3 of the distance? And what we do there, we do over here, and we're like, okay, fine. Swoop, there he is. Now question. We already have the vertical shrink. Okay, not quite like this. Adrian, what else changed besides this vertical shrink by 1/3? The 1/3 made it wide. It pushed it down.
It went down.
It went down. So it didn't just have a vertical shrink by 1/3. We also have to add one more piece that happened. When we graphed it, we also saw a vertical. Guys, the terminology is not crazy. Vertical shrink by 1/3 and a vertical flip. Now there is a snazzy, Max, I see that hand. Give me one second. There is a snazzy math term for flipping, and it's called reflection. Like in the mirror, your image is there but flipped. Yeah. There's a reflection across the x-axis. There is snazzy terminology, but for right now, before Thanksgiving break, we're just going to say, you know what? There was that vertical flip with that negative dude, and there was a vertical shrink pushing down on it by 1/3. Actually, there was kind of like a shrink and then a flip. I guess you could have done a flip and then a shrink. But we're going to use some of this terminology to describe what happened. Max, go ahead, buddy. Yeah. I was trying to show you guys all of it at once. Let me zoom in right now. All right. Once you guys have this page written down, I will show you once again that second half of section 8.1 homework. But if you look at the clock, we have 10 minutes, and we have some factoring to try to master. Not master, we're just polishing. Polishing today. Like, we worked on it. It's pretty good. It's gonna, right? If you wash your car, you just do that last little, like, polishing, waxing it off a little bit. Yeah. We're gonna try to polish it right now. But to polish it, I need you guys too. Alyssa. Hi. Alexis. Hi. My voice is dying, and I still have 4 more classes to teach. Turn to the back of your homework spiral. Let's get into our workspace, because we're gonna work. Not in a way that we're learning, but in a way that we're practicing, okay? Factoring for tomorrow. Everybody, look around. If anybody in your group is struggling, just kind of give them a nice little gentle little, like, hey, time to wake up. Give them a high five. Give them something. Gotta go fast. I want you to get All right, back in your homework spiral. Factoring practice. Okay, if we had tons of time, we would make this a group competition. But we only have like 9 minutes. So we're going to work together as a whole class. However, I am not going to hit the button for submit. We're going to work together as a whole class. Competing as a whole class. Trying to, well, win a pretend $1 million. We're going to try to win a pretend $1 million. But guys, I am not going to hit submit until we have work shown as to why the answer works. Because tomorrow on the test, I don't want you to go real fast and be like, I got the answer, and then move on. I want you to make sure it's right. And there is one way, and one way only, that you can make sure it's right. And it's called multiply. And we all did it in section or chapter 7A test, and most of us, the multiplying part was the easiest part of the whole test. Remember the sum and the difference and the polynomial and the degree and all that craziness. Okay, so we're going to make sure that it's right first. All right, you guys ready? I'm going to zoom in a little bit because it's kind of zoomed out. I'm going to try to zoom in a little bit. If we get it wrong, we have to go back to the very bottom. If we get it right, we're going to move on and move up.
$1 million.
Ready? X squared. Write it down. Are you sure? Tomorrow, are you matching?
I'm so positive.
Why are you so positive?
It's amazing.
X squared minus 3x minus 2x plus 6. How am I multiplying? I'm multiplying with FOILing because you also put a box to check. Yes. Does it work? Does negative 3 plus negative 2 make negative 5?
Yes.
Looks good to me. But if you were solving, would you have thought of 6 and negative 5, and would you have gotten to negative 3 and negative 2?
Yes.
I hope so. All right. Hey, let's see if there's another one that gets harder.
Come on.
Yeah. Oh, got $300. B.
B, for sure?
Yes.
How could you check?
7 times 5 equals 14.
X squared plus 2x plus 7x plus 14. Does it work?
Yes.
Yes, we'll check it with the box next time. But question, guys, what would have gone in your x off to the side from that guy? Looking for factors of 14 that make 9. Would you have gotten 2 and 7?
Yes.
Okay. So we think that it's B. Got him.
400.
Woo!
Yay.
16x squared minus 225.
C.
I heard an A, I heard a C.
C.
Study.
C.
Pay attention, Andres. I don't even see your eyes. How can you be learning? Here you go. I hear an A, I hear a C, I heard a B.
C.
Has anybody square rooted 225? Did you guys figure out how to do that on the calculator? It can be nice. There's a square root button. It looks like this. Would you have gotten it to have been 15?
Pretty sure it's C.
Okay. Question. What would you have put in your x? I'm just saying we have different answers, which means some of us would have gotten this wrong if we had done it really quick on the test, right? So, what would go in the top of your x?
16.
Not 16 and not 225. 16 times 225. 16 times 225. Does anybody have that off the top of their head? Probably not. It's a hard one. 16 quarters. Wait a minute. That'd be 4 sets of 4. Wouldn't that be 400? Oh no, 225. Sorry, way bigger. I was thinking 25. 3,600. For question, what would go on the bottom? What was that? 0, because there's no middle term.
Yeah.
Now, there's always a shortcut to these guys if you use this button. Maybe some of you know that whole a squared minus b squared shortcut. Oops, minus b. My bad. Shortcut, and that's how you went to the answer real fast, aka b and d are definite no's. You need a plus or a minus to cancel out. But if you do the correct a times c and square root it on your calculator, guess what the square root of 3,600 is? Ooh. Neither one has 60. Oh, because RX gets us to a box. And the box would say 16x squared and 225 and a negative 60x and a positive 60x. So when you factored out, you would end up with being able to pull out a 4? A 4x that way and this way. You might have to use your calculator a little bit. And then what comes out this way? A 5, 10, a 15. Thank you, Taylor. That's perfect because I needed it right about now. So what's the final answer, guys? C. Oof. Did anybody find one on the test that they were doing corrections on with like a 3 and a 10 and a 13? And
Oh.
or maybe like a 16 and a 9 and a.
See.
Wait, no, not
You
C.
take the 3 out.
I know, because right now I'd have to do 3 times 243. That's 729. This is going to take forever. Some of you freaked out with 24 on the test, and that was hard. If you get all the way down to 12, it's not good. But Alexis, what did you say we should probably try first?
Take the 3 out and then you divide
The
it.
3? Wait, 3 goes into 54?
Yeah.
Oh yeah, 18 times.
Yeah.
3 goes into 2? Thanks, Isaiah. Not quite sure. They're totally tracking. I mean, not exactly sure you're right.
Oh.
Not questioning, I'm just saying. Right.
Oh, not even.
Pulling out a 3 makes the number smaller. Hey, what goes in your X now? Oh, we still have to factor? Yeah. But can't we say A and C are both wrong because they don't have 3's?
Yes.
What goes up top?
Really? What?
What goes down bottom?
C.
9 and 9.
Oh.
So then
It's D.
we could go ahead and do our factoring, but we are going to end up with, it was a positive 9. And the negatives don't make sense. I don't see any. Be careful. Some of you have been doing this in homework where you make it match and you don't really know how to get there. So even if you're making these match perfectly, you got to watch out that you know how to get them yourself tomorrow. No, that's why I'm warning you, right? Yeah. Let's go ahead and make an X with a, no, Alexis, we need you. What should we do first?
Take the 2 out.
If you see a GCF, take it out because life gets a lot easier, right?
Wait, why you saying?
And maybe just a few of you might be able to make the final match not take too long on it. Careful, it's not 6 and 1. I need the same sign. I need them both to be negative. So I need 2 and 3 to add to be 5, or negative 2 and negative 3 to add to be negative 5. So pretty quickly, maybe some of you would be able to match it to A, but hold on. I need us to get to a trickier problem. Here we go. Everybody, is there any GCF?
No.
So what's going to go in the top of my X? 30. What goes down here? As you guys are pondering, doesn't still that first term go right there? Doesn't this last term go right there?
Yeah.
15 and 2, right? Now, pause. How does the box method work? What's in common? Follow my finger. What's in common? X. What's in common? 3 and X. What's in common? And what's in common? Would you have made, which one, the right match?
B.
Now wait, Tamara, are you matched?
No.
No. But what is the test gonna look like? The one we took last week. Factor, solve. Oh no, solve. Factor and then the parentheses. Bye guys, any questions? Right on top, your guys.
I'm not even doing that.
Good job guys, work on your factoring tonight.
Now